Hello guys, welcome back to my channel Gamma Di Gamma. So first of all, Happy New Year. And I'm assuming it may not be the new year when this video gets uploaded from your part of the world. But nevertheless, this is my New Year's gift to you guys. So in the previous video we talked about eigenvalues and eigenvectors, and this video is sort of like an application of eigenvalues and eigenvectors. And let's get started. Okay, so to start with, we have this situation. We have two blocks of mass m1 and m2, and they're connected. So m1 is connected to the fixed support or the wall with a spring of spring constant k, and the two blocks are connected in between with a spring of spring constant k prime, and then the wall condition of m1 is repeated with m2 with a spring that again has a spring constant k. So we have to basically characterize the motion of both masses m1 and m2, basically write equations for them. So for that, we're going to use Newton's second law of motion, which is that the net force on a body is equal to mass times acceleration, and acceleration can be interpreted as the second derivative of position with respect to time. Okay, looking at block of mass m1, the external force, assume it's like displaced by a value x1 from, say, its rest position. Well, at that point, when that displacement happens, the net force acting on mass m1 is the restoring force by the spring, and restoring forces by springs are given by Hooke's law. Negative the spring constant, whatever that may be, times the displacement. So in our case, this is the external force, total external force, and then that will equal mass times the second derivative of displacement, which we denote as double dots, x double dot. Okay, now writing the equation for the restoring force is a little tricky, because notice there's the restoring force by this first spring, fine. So that will be negative k times whatever displacement x1. Negative because if we displace by a positive x1 to the right, the restoring force will be directed inwards. Fine, and then the restoring force by the second spring, because it's directly connected to the first block. Now the intermediate spring is a little bit tricky, because we also have to take into consideration the amount of displacement that this block m2 has from its rest position. Because think about it this way, if x1 and x2 are equal, then there is no compression or extension of this intermediate spring. So therefore there will be zero restoring force due to from the middle spring. But if x1 is greater than x2, there's going to be a compression. So the spring will basically again push to the left like we had with the first spring. So to denote that, we have to write x1 minus x2 with a negative sign, because when x1 is greater than x2, this term is positive, and then this total term k prime x1 minus x2 with a negative will be negative, because this inner term is positive. And that's, as I explained, will help us denote that the restoring force is acting to the left. And then this makes sense, because you can check if x2 is greater than x1, then there's like a net elongation in the spring, and the spring is going to basically, the restoring force is going to be directed towards the right hand side. So the sign is going to flip. And that by Newton's second law is mass times x1 double dot. Fine, that's equation number 1. Now we can do a similar thing for block 2. This time instead of x1 we take x2. Negative k x2, because the restoring force will be directed this way now. Restoring force by this inner spring. And then a similar thing for the k prime, except we have k x2 minus x1, because if this feels a force directed to the left, this will feel a force directed to the right, and the signs flip basically. And that by the second law of motion is, this is m1 and this is m2. Forgot to write the masses. x2 double prime. Fine, we have these two equations. Now what I'm going to do is I'm going to isolate this x1 and x2. So x1 double prime is negative k x1 over m1, negative k prime x1 minus x2 over m1. x2 double prime is going to be negative k x2 over m2, negative k prime over m2, x2 minus x1. These are the two equations. Now I would like to represent them in a matrix form, just for convenience, because we have two equations. Let's write them in a matrix. So capital X double prime, and capital X I'm defining as x1 double prime, x2 double prime, this column vector basically, is equal to, now we need a matrix here, and if we group some terms properly, we're going to get negative k plus k prime over m1 x1 plus k prime x2 over m1. I'm just isolating x1 and x2, and then here we'll get k prime over m2 x1 plus negative k prime over m2 x2. So I can write them in a matrix now. Negative k plus k prime over m1, k prime, negative k plus k prime, forgot the m1 and the m2 here, and then we have this entire thing applied to this vector x1 x2. Now this x1 double prime I can represent as the second derivative with respect to time of the column vector x1 x2, and then this is just the same. So we have this interesting matrix vector system. It's like one of those linear algebra problems, linear transformation T, which can be represented in terms of a matrix. T is equal to AX, for example, and A is basically this matrix. This is one of those systems. So it's interesting how we can convert a bunch of linear equations that we got from mechanics, laws of mechanics, into these matrix vector systems, these linear transformations sort of. And now, before moving on, I would just like to state that in case you were wondering why I didn't start measuring or didn't take my origin to be this wall, for example, and whether that causes any change to happen in my equations. Well, it doesn't, because if I take this to be the origin or whatever, then I would have to add like a rest length every time. So L naught x1, like L naught x1, and then whatever dynamic length of this spring that was in between, and then x2. I'll have to keep adding all these unnecessary constants. And why I say it's unnecessary to add them is because we anyways gonna subtract when we take the change in displacement. I mean, there's a subtraction here, there's a subtraction here, so anyways those guys are just going to cancel out. So you can just consider this displacement from each of their respective rest positions instead of just taking the wall to be the origin. I mean, that's like a little insight you get by experience, and it doesn't change the equation. So that's why this approach is valid. Okay, let's move on to the next part of how to solve this or whatever. Okay, so we have this system, matrix vector system or whatever. We have this thing now. What do we do with it? How do we simplify it into stuff that we can solve actually? I mean, this doesn't make any sense at all. I mean, what the hell is going on? Well, if only we could, we can write this as A times X. We can call this matrix A and this vector X. If only we could decompose this to get lambda times X, or instead of X, I don't know, just call this another vector, maybe V or something. Maybe just call it like X tilde or something. Okay, X tilde is equal to lambda X tilde. If only we could decompose, and lambda is a constant. If only we could decompose this system of A times X tilde into lambda times X tilde. If only we could do that, this would make so much more sense, because then we have, well, the derivative, looking at the first entity, the derivative of x1 with respect to time taken twice is equal to some constant times x1, and that is a perfectly solvable ordinary differential equation. If only we could convert our system into some constant times whatever initial vector we had. And looking at this and comparing that to the previous video I had put up, this is an eigenvalue problem. I said x tilde because we need to put some conditions on this x1 and x2 in order for us to be able to successfully decompose the problem in this form. So for that, let's calculate the eigenvalues. So A is this matrix. To calculate eigenvalues, the first step we took was determinant of A minus some unknown constant lambda times the identity was set to 0. I explained that in the previous video, so please watch that before coming to this video. And when I do that, I have negative k plus k prime m1 minus lambda k prime over m1 k prime over m2 negative k plus k prime over m2 minus lambda. And while the determinant of this guy, this matrix, was set to 0. And if you try computing the determinant all on your own, you end up with this characteristic equation. So lambda squared plus lambda times k plus k prime over m1 plus k prime over m2 plus k prime whole thing squared over m1 m2 minus k prime squared over m1 m2 was equal to 0. If you use the quadratic formula, because that's the only savior we have right now, we get values of lambda as negative k plus k prime over m1 plus k prime over m2 plus and minus the square root of k plus k prime over m1 plus k plus k prime over m2 whole thing squared minus, gosh, this is gonna be big, 4 times k plus k prime squared over m1 m2 minus k prime squared over m1 m2, all of this under one big square root, and we still have to divide by a factor of 2. This is the general expression for an eigenvalue of this system. And if you have same masses, m1 is equal to m2 in that special case, this just reduces down nicely. Since we're physicists, we don't necessarily care about those conditions first. Let's solve it generally. So lambda plus is going to be the positive branch of this, where you ignore the negative, just have a positive. Lambda negative is going to be the negative branch of this crazy expression. I'm going to address them as lambda plus and lambda minus, because this expression, it takes the breath out of anyone who tries to write it out again and again. And I don't know, this notation is a little weird, but it's funky because this makes lambda seem like ladder operators from quantum mechanics, but well, their function is essentially the same as ladder operators technically when we try to convert every differential equation into a linear transformation, but whatever, I like this notation. So these are the eigenvalues that we have. Okay, fine, we found our lambda, but what about the x tilde? What condition should we have for x? Let's figure that out on a fresh page. Okay, try to figure out the eigenvectors for this system. Well, we basically need to find the null space of a minus lambda plus I. Okay, so for doing that, a minus lambda plus I just becomes the matrix negative k plus k prime over m1 minus lambda plus k prime over m1 k prime over m2 negative k plus k prime over m2 minus lambda plus. And now we need to find the null space of this guy. So just basically try to convert this into some row echelon form. So what we can actually do is divide first the entire first row by this crazy expression over here, 1 k prime over m2, and then over here we end up with a negative k prime over, let's see, k plus k prime plus lambda plus m1 if I'm not wrong, and then here there's another. I think we can keep this guy the same. And now we want to make this bottom entry 0 in the first column. So we have this first entry as it is. Now the second entry just becomes a weird expression, k plus k prime over m2 minus lambda plus k prime squared over m2 k plus k prime plus lambda plus and then m1. Okay, now fine, we got one pivot. Now we don't want a pivot in the second column. So we would get a pivot in the second column if this entry was non-zero, in which case we could just divide the entire second row by this entry and get a 1 here. This guy, if this the bottom guy is non-zero, then we have pivots in every column. This will reduce to the 2 by 2 identity, and then our eigenvector will just be the trivial case, which is the null vector 0 0, and we don't want that, right? If we find eigenvectors, the 0 0, the trivial case, is the most unwanted situation ever. So this means we have to assume that this bottom guy is 0, and is a pretty valid assumption, at least in this problem. So if this is 0, we just have 0 and 0 here, and negative k prime over k plus k prime plus lambda plus m1. And now finding the null space is easy, and when we do that, we get the first eigenvector corresponding to lambda plus, and that just becomes 1 k plus k prime plus lambda plus m1 divided by k prime. And the best part is we don't need to do anything special for the lambda minus case, because just replace the plus with the minus, the steps were the same. And again, we make a similar assumption for the lambda minus case, except instead of a lambda plus here, we have a lambda minus there. So this becomes 1 k plus k prime plus lambda minus m1 over k prime. Okay, so now going forward with whatever we were doing, we had system ax tilde is equal to, I don't know, some lambda x tilde, which was basically this matrix vector multiplication. And using the properties of eigenvalues, eigenvectors, we can break this down, at least this guy, we can break down first into lambda plus and its corresponding eigenvector, which is v1. Lambda plus is lambda plus. v1 we calculated to be 1 k plus k prime plus lambda plus m1 over k prime. So this is the condition we have to set on x1 and x2, because now x1 and x2, or actually the ratio between x1 and x2, it's best to put it that way, is equal to 1 over this guy, which will be k prime, k plus k prime plus lambda plus m1. So now this puts this constraint on x1 and x2, at least for this case, the lambda plus case. We can also break this down into lambda minus and v2 vector. So lambda minus 1 k plus k prime plus lambda minus m1 over k prime, and we get a similar condition over here. x1 and x2 for the second case should be in a ratio k prime over k plus k prime plus lambda minus and m1. That's the condition if we want to successfully break our system down into this. Okay, now let's solve for each successive cases. So let's solve for lambda plus case, because this, if x1 and x2 satisfy this condition, can be broken down into lambda plus times this eigenvector, but all of that is still equal to the second derivative with respect to time of x1 and x2. And since an eigenvector, we can take an eigenvector to be any scalar multiple. We can take any scalar multiple of this basic eigenvector. So let's just multiply by a constant x1 throughout for both entries. Again, x1 is just a constant. And now let's try to solve this first equation over here. So the top entry now becomes the second derivative with respect to time of x1 is just equal to lambda plus an x1. And well, this has a simple solution. x1, which will be a function of time, certainly, will be a which is some scalar, times e to the square root of lambda plus times t, plus b times e to the negative square root of lambda plus times t. Fair enough. Okay, now solving for x2. We have lambda plus, and then this factor that we didn't have originally, which is, I believe, k plus k prime plus lambda plus m1 over k prime, and then an x1. To be honest, we actually don't even need to solve for x2 because we got x1 and x1 was the multiple we desired. So the first system just becomes, well, x1, x2 is equal to a times e to the square root of lambda plus t, b e to the negative square root of lambda plus t, and then apply it to this vector 1 k plus k prime plus lambda plus m1 over k prime. Well, that's for the first eigenvalue. For the second eigenvalue, if we use a similar approach, we get some new constants this time, c times e to the negative lambda minus t plus d times e to the negative square root lambda minus t, 1 k plus k prime plus lambda minus m1 over k prime. We get a solution like that. And since it was a linear system all along, the general solution will be a linear combination of these guys. So if we call this a prime and b prime, just changing names for the sake of notation, you're finally going to end up with this grand answer, which is a times e to the square root lambda plus t, b times e to the square root lambda negative lambda plus t, 1 k plus k prime plus lambda plus m1 k prime, added with c times e to the square root lambda minus t plus d times negative e to the square root lambda minus t, 1 k plus k prime plus lambda minus m1 over k prime. And that can be considered a general solution. And now on further inspection, you notice that lambda plus and lambda minus are like the two fundamental frequencies of this system. you can interpret them as normal modes of vibration. And this concept of having fundamental frequencies to system is, basically the entire theory of quantum mechanics. Finding these eigenvalues of systems and operators helps us solve many problems in quantum mechanics. And it's interesting to see how if you take m1 is equal to m2 is equal to some m, the lambda plus we get is I think negative k, and lambda minus we get is negative k negative 2k prime over m. And then this basically breaks down into sine and cosines, because then the square root of minus becomes I, and you can write it as a series of sines and cosines. And essentially even this breaks down into 1 1 and 1 negative 1, these eigenvectors. And that's how you know when, if it's 1 1, that means like the blocks are in phase, they're moving to the right together or to the left together. And when the eigenvector is 1 minus 1, that's when they're moving out of phase 180 degrees. So one's moving to the right, the other's moving to the left, and vice versa. And when that thing happens, that's when the modes of vibration, the normal modes of vibration change. So for when if they're in phase, then it's lambda plus frequency of both, and then if they're out of phase, it's like lambda minus. And since it's not going to be one pure movement of in phase and one pure movement of out of phase, it's going to be some combination of like in phase, like this will they will be in phase like 3 times as much as they will be out of phase or something like that. So it's gonna be some weird motion which can be expressed as a linear combination, like we did here, of these fundamental frequencies. And you see how eigenvectors and eigenvalues actually helped us. They helped us decompose this complicated matrix. We got rid of the matrix and got a scalar in place, imposed some conditions on x1 and x2, and that helped us solve our problem efficiently, because then we just end up with a ODE, which is pretty easy to solve if you compared to what we had before. So yeah, I hope you enjoyed this video, guys. So please like and subscribe to my channel, guys. Recommend my channel to your friends in the math and science community. And in the meantime, stay home, stay safe, keep doing math, and peace out.